This is my public PhD defense of my doctoral thesis. The title is Debloating Java Dependencies. This is what I've been doing in the past years. My name is Cesar Soto Valero. I am a PhD student from the ATH. I am supervised by Benoit Badri and Martin Monterus. And I am also a BAS PhD student. BAS is the largest research initiative in Sweden, funded by the Wallenberg Software Foundation. And during these years, I have been also part of the Castor Software Research Center, which is an initiative to bring collaboration between academia and industry. So, Gerald Hoffman, which is a very well-known computer scientist for his contributions to formal methods and program analysis, he wrote an article in 2015 called Code Inflation, very influential. He wrote the article and published it in IEEE software. And I would like to quote one sentence in this article that says that software tends to grow over time whether or not there is a need for it. In this publication, Holzman explained the case of the true Linux command, which just increased over time without almost no reason. And yeah, he makes the point very well. And this sentence summarized this phenomenon. But this is something that not only happens for small programs, but it happens very much for the large systems. What you see is an example of the numbers of lines of code in the Linux kernel for the time range of 25 years. This was published by the Linux Software Foundation, and as you can see, the increase is almost linear. It's a constant increase in the number of lines of code, and in 2016 it was 22 million. So there's a lot of code there that is developed, maintained, analyzed, compiled, and deployed. And this process is quite complex, and we have the intuition that there is code there in the Linux kernel that it may be unnecessary. But that is very hard to detect. It's very hard to surgically isolate this piece of code and then separate it from the rest and remove it. So it's really very complex in such a large system to get rid of unnecessary code because of the complexity of the software development process. So this leads to a phenomenon called software bloat. And software bloat refers to code that is packaged in an application. In the previous example, it's like code that is packaged in the Linux kernel. But it is actually not necessary for building or running the application. And software bloat is a problem, first of all, because it needlessly increases the size of the application. And this could be a problem, for example, in environments where size is a very strong constraint. Think about mobile devices, or think about IoT devices, where space is an issue. But today, due to cloud computing, for example, space is also something that you need to pay for. So size is something that is important to get in control. And it is a problem for maintenance because developers have to deal with more code. If you have more code, if you have code that you don't need, then it's a problem because you want to really understand and have full control over the code and make sure that the code that you have is the code that you need. So this is very important. And of course, it's also a problem for performance because having more code, for example, more dependencies, meaning pulling more data from the internet and increasing the bandwidth. And for example, there are applications that actually need to get very fast, to execute very fast, and it's very difficult to get performant code if you have a lot of code that you don't need. And very much, it's a problem for security as well, because more code is, as we know, more likely to have bugs, and more bugs it leads to vulnerabilities, and vulnerabilities is the source that the attacker wants to compromise your system. So software bloat is a problem for security, and we need to take care of it. So in order to address this phenomenon, the research community, along practitioners, have created techniques called software debloating with the aim of mitigating. So software debloating is the process of automatically detect and remove software bloat across the software development lifecycle. This is our definition of software debloating, and notice that we include the term software development lifecycle because we think that software bloat is something that needs to be tackled across the whole process of software development. And there are 3 papers that I love about software debloating. The first one was published in Unused in 2019. The title is Razor, a framework for post-deployment software debloating. And this paper is relevant because it performs code reduction for deployed binaries. And it does it, or it debloats 2 really large software applications, the browser Firefox and 4C Reader. And the authors demonstrated that they could reduce the size of this application in 70%, which is really impressive. The second paper that I love is titled Selenium, Debloating the Chromium browser with features of 7. And this paper is influential because it performs feature debloating. So it focuses on determining which features in the Chromium browser, which is a really big and complex piece of software, is an entire engine. And then, given these features that they want to debloat, then using dynamic analysis, they run the Chromium, they perform the debloating analysis, and then remove the features that were wanted. And they achieved 21% of code reduction in Chromium, which is actually a milestone. And the third paper was published in TSC in 2021, and the name is Trimmer, an automated system for configuration-based software debloating. This paper is very strong, and it was targeting binaries based on configuration files. So it used configuration files in order to determine which pieces of the software application were not part of the pieces that were needed for the software to execute and to deliver a given functionality. And it was evaluated in 20 applications for the Linux command line applications, and they managed to remove 14% of the binary in those applications. So these 3 papers are very good. They are milestones in the software debloating areas. But there is something that they have in common. The first thing is that all of them target binaries. So they target programs that were already compiled into an executable file. And all of them also mainly focus on security. So they focus on debloating with the purpose of removing vulnerabilities from this from the application that were target of the debloating. So, but as we know, the software development, as I mentioned earlier, is much more complex than that. And today, this is how it works. Normally, it starts with a team of developers. Yes, there are humans today still. And then there are three key phases in this in the development process. The first one consists in implementing the feature or implementing the piece of software that complies with the requirements. And in order to do this, the developers communicate and use different tools. And the output is normally source code and configuration files. And these source code and configuration files, they go into a build system that checks that the software is compliant with what it is supposed to deliver. And then there is a compiler that compiles the source code, bundle all together, and then is ready to be released and deployed. And the final destination is to be running in a running environment. It could be, for example, in the cloud or some other device, for example. And as I mentioned, in order to do that, developers reuse tools, for example, IDEs, issue trackers, and so on. And in all the phases, they reuse these tools, compilers. Infrastructure as code is something that is quite popular today with Docker and other orchestration software. But there is something that we see across the whole pipeline, and this called software dependencies. And software dependencies they are applications that they are code that is packaged, is reusable components, reusable software components, which are part of the whole development lifecycle. And the way software dependencies are managed today is through package managers. Package managers exist for all programming languages. For example, for Java, there is Gradle, there is Maven as well. For Python, is EIP. For ROS, Cargo, and JavaScript has NPM and so on. And dependencies exist in software repositories. So software repositories host these dependencies where package managers pull them and put it inside the software development lifecycle. And they are part of the whole process, especially in the deploy phase where the code is bundled and then deployed as well. And there is one thing that, as we have observed, could happen, and is having bloat across the whole process. It could be bloat in the code itself before compilation. It could be bloat in the compiled output of the code. And it could be bloat, of course, in the dependencies as well, because the dependencies are software. So the dependencies could be a source of bloat. So this situation leads to three problems. The first one is the increase in the supply of software dependencies. that leads to dependency bloat. In our case, we focus on this problem in the Java ecosystem. The second problem is that most of the code shipped with the dependencies that are actually used, that has some part that is used. It could be that some of this code is unused by the software project that depends on it. And also, that the bloating software libraries could affect the clients that depend on this library. So you have the library, and then you have a client, and if you debloat the library, this could affect the client. And today it's not clear to what extent this is a problem. And in order to address these three problems, we have some contributions. So we have three contributions. The first one is about removing bloated dependencies. The second one is about specializing the dependencies that are used. And our third contribution is about debloating with respect to clients. And for this contribution, we use code coverage analysis and debloated using dynamic analysis. But in this presentation, I'm going to focus on the first one only, because it could be too much. So let's talk about removing bloated dependencies. So this is a class which is part of Apache Spark. Apache Spark is a very popular Java project for large-scale data manipulation, and it has one method called parse ignore case, which contains 2 parameters. And what is interesting is that Apache Spark uses this class, joiner, and it has 2 static methods, on and join. And what is interesting is that these methods that come from the class joiner are imported. So they are imported from a package named com.google.common.base. And this is the source code. This is what developers see, what they program. But once the previous class is compiled using the Java C standard compiler, you get this class, a new util.class. And as you see, there are 2 invocations. There is one invoke static to the method on in the class joiner here. And there is also another invocation to the method join in the same class joiner. And this class is part of the library, which is contained in the library called Guava, which is part of Google. So this code, which is part of Spark, actually is not written by the developers of Spark. It's written by Google developers, who shape this code as to be reused for everybody, and now it's part of Spark. Now when you compile, as you see, this is the actual code that is executed by Spark. And this is the bytecode of the method on, and this is the bytecode of the method join. And these 2 methods, what they do is just joining a string. So they just join, do the merge of the string variables. But the key thing here is to know that this bytecode is executed and is part of a dependency, which is Guava, and is part of Spark. And today, Spark is really a big project. So I just counted a few days ago, and the number of lines of code I actually, sorry. The actually number of lines of code in Spark which are compiled to Java bytecode is almost 1 million. So this is the lines of code. But once this code is compiled, is more than 50,000 methods and is more than 3,000 classes. And all of this have the addition of 529 dependencies, which are handled by Maven, which is the build package manager of Apache Spark. And what you see is really a representation, but it's a real representation as a picture of the dependency tree of Apache Spark. And there, Guava is just one tiny node. So as you can see, this is very complex. And for developers, in order to handle this complexity is really difficult. And this is why dependencies are becoming something that developers need to pay attention to this, because if they are really massive and increase the complexity, and in order to analyze this complex dependency trees, we need tools and we need techniques. Yes, this is the representation of the dependency tree. Let's say for a general project P, you have, in the case of Java, in Maven, you have 3 dependencies. In this case, there are dependencies A, B, and C, which are declared by the developers of the project P in something called the pom.xml. And pom.xml is a configuration file where developers declare the dependency that they intend to use. It's very interesting that by declaring dependencies, the developers of this project P also are gonna get dependencies D, E, and F, which are going to be pulled by the build engine every time the project P is built, because the dependency D and the dependency E are necessary, are part of the dependency A, and the dependency F is also part of C. So in Java, in the Java Maven ecosystem, there is also a parent relationship in which a dependency could be inherited. So in this case, the project P declares Q as a parent, and then the dependency G is declared by Q, and then it becomes automatically a dependency of P as well. So this is a very specific Maven dependency relationship, but it is also important. So in summary, there are 3 different cases. The first one is the direct dependencies that are declared. The second one is the transitive dependencies that are induced by declaring direct dependencies. And the third case is the inherited dependencies that a project could get from dependencies that are declared in the parent project. So what I showed you before is what happens in the dependency tree. It's in the configuration file. It's the analysis that is done by the package manager. But actually, what the project needs is the code. It's the code that is in the dependencies, where it is executed. And in order to know which code is actually needed by this project P, we perform a static bytecode analysis. Remember, these dependencies are already code that is compiled, so it's compiled code. So the only way is to analyze in the bytecode, doing bytecode analysis. And this is part of our contribution, is this technique to analyze the dependencies of software projects. And first, we analyze all the code in the project, all the compiled code in P. So we analyze statically all the types there, all the methods, all the attributes, and then, after this analysis, let's say, for example, we found that there is one part in the project P that needs another part in the dependency A. And then we found that there is another part in the project P that it doesn't need the dependency B or C, which are the source of F. Because remember, F is a transitive dependency that was pulled from this dependency. But the project P directly reuses some part in F. And this we determine it by using a static analysis. So we build this tile graph of types, and then through this analysis we found that the part in A that is needed by B also have another part in D. So we don't analyze the whole A in this case. We only focus in this piece here. So we analyze in this piece, which is the actual use, which other elements are necessary. And in this case, it's only one element. So this is the result of our static analysis. And as you can see, once you have this knowledge about the parts in the dependency that are actually necessary, then you can proceed to remove the dependencies that are just bloat. And in this case, for removing the direct dependencies, is just removing the declaration in the POM file. So it's removing the entry files to this XML, POM.xml document. And in order to remove the transitive dependencies, this is done in Maven by adding an exclusion clause in the entry of the direct dependency, which contains this transitive dependency that is necessary. It analyzes the whole dependency tree. So do you remember the previous example of Spark with the really huge? So Debloating analyzes these all dependency trees. It looks at all the bytecode elements there in order to determine which of the nodes are actually necessary for Spark to be. And then, after the analysis, Debloating generates a POM file which doesn't contain bloated dependencies. So we remove the bloat from the dependency in the dependency tree. And Debloating is an open source project which has been well accepted by the community. It's a popular project in GitHub, and we have received very good feedback. It's something that I'm proud of, to have this project as a result of my PhD. And we use Debloating. We use Debloating to actually develop Maven projects. And this is an example. It's the Spoon library used for meta-programming. And we use Debloating to remove 13 dependencies in Spoon. We submit the pull request, and the pull request was accepted. And as a result of these two requests, we remove 28% of the jar size of Spoon. And this is very good because then the clients of the Spoon library, once they need some functionality from Spoon, then the jar file that they are going to pull is going to be smaller. And this, as we saw before, is very good to have this size reduction. And this also means removing 25% of the classes in Spoon, which is also good because it decreases the attack surface. So having less classes, it means having less executable code from a library like this, which is good for the community. So now the question is, how much dependency bloat exists out there? In order to answer this question, we performed an empirical study, really large scale, based on data that we collected in 2019 from when we were doing a paper for the MSR data showcase, in which we did something that we call the Maven dependency graph, which is a graph of all the relationships between artifacts deployed in Maven Central. Of course, we cannot analyze the 3.6 million artifacts there, because that would be too much. But we filtered this, and we analyzed 9,000 artifacts that we found. We choose a criteria for this, for selecting these artifacts, because we found them to be diverse, reused, and complex. And this means 723 dependency relationships that we analyzed with Debloating. And most of these dependency relationships are transitive dependency relationships, 69% of them actually, and 25 are inherited dependency relationships, and 6% are direct. And this is the result that we obtained after analyzing all these artifacts with Debloating. We were amazed to see that 2.7% of the direct dependency relationships are bloated dependency relationships. According to our tool, 15% of the inherited are also bloated, and 57% of the transitive dependency relationships are bloated. So the takeaway here is that dependency bloat is actually something that exists, and it exists at the scale of a repository. And it affects, in our case, we found that it affects 75% of all the dependency relationships that we analyzed. So now that we know that bloat exists, that it's actually something that has a scale, the question is, do developers care about bloated dependencies, having bloated dependencies in their projects? And in order to answer this question, we performed a user study on 30 software projects, very popular in the Java ecosystem. If you are into Java, you probably will recognize Sextile, MyVertis, Jenkins, Neo4j, so on. We analyze these projects. We submit pull requests to developers suggesting the removal of bloated dependencies. And we receive a positive response in 21 pull requests, which were accepted and merged. And only 5 were rejected, and for 4 pull requests we didn't receive a response. But in total, we removed 140 bloated dependencies in 21 projects with Debloating. So the takeaway from this experiment with developers is that they are actually willing to remove bloated dependencies from their projects. But during this interaction with developers, we entered into a discussion of why considering debloating, why debloating is important, why should they remove bloated dependencies. And there were some comments from developers. For example, this is one comment for a developer from Jenkins. In particular, we were discussing debloating dependency in Jenkins code, and this is what one of the developers said. She said, past experiences removing unused dependencies have consistently shown that some code will have depended on that inclusion and will be broken up. So it means that developers have concerns that by removing a dependency in the project, it could be another project, perhaps within the same organization, that actually needs this piece of code. But how to know if this code is being used by someone else, beyond the code that you can analyze. So, as we could see, this could be tricky, and also, they don't know if the dependency that you remove today is going to be needed in the future. So how to know that this dependency is not going to be reused again in the future after being removed? So it's very hard to know. Actually, what we did was perform a longitudinal study in order to answer this question. Actually, we analyzed 435 projects. And we analyzed the status of the dependencies in all the versions of the dependency trees of these projects in order to answer two questions. The first one is, do bloated dependencies stay bloated across time? So we have different versions of the dependency tree, then we analyze those, and then we determine this dependency, which was bloated in this version, is still bloated in the further versions of the dependency tree, yes or no? This is the question. And the second question is, do developers maintain dependencies that are bloated? So let's say that you have a dependency, but this dependency needs to be maintained. But since the dependency is bloated, it means that this maintenance is kind of waste of human effort. So this is the result of the first question. In order to get the answer, we create patterns. In this case, we have 5 patterns. The first pattern is labeled by B, you can see, and it means that the dependency was bloated and it stayed bloated in all the versions of the dependency tree. The second pattern is labeled by U. It means that the dependency was always used from the beginning of the analysis of the project. And we have transitional patterns. The first one is VU, which means that the dependency was first bloated and then used. This is the concern of the developers, actually. And the other pattern is UB. It means that it was used and then bloated, and we have some fluctuation. Where is actually the key result here is that 93% of the dependencies that we analyze, actually, they doesn't change. They keep the same status. They are either used or bloated. And this happens for direct dependencies and for transit dependencies as well. So, in summary, that means 89% of bloated direct and 93% of the transitive bloated dependencies remain bloated in all subsequent versions of the dependency trees for the study purpose. And the takeaway is that to answer the developer's concern, we believe that bloated dependencies remain bloated over time. And then we address the second question, which is, do developers maintain dependencies that are bloated? And in order to answer this question, we analyze a specific maintenance task performed over dependencies, which is updating the version of a dependency. And in this case, we focus on commit diff that change the version of the dependency. In this case, is the update of commons.io, a dependency, from version 2.6 to versions 2.7. And this is performed by developers, like it's very common maintenance task. And this is the result that we obtained. Very interestingly, 22% of the commits performed on the projects that we analyzed, which were about updating dependency versions, were performed on dependencies that are actually bloated. So the takeaway is, yes, developers maintain dependencies that are bloated. So now I'm going to wrap up the conclusions, and then I'm going to refer very briefly about the lessons learned during my PhD, and then I'm going to talk about the other contributions. So in conclusion, we found that Maven dependencies are bloated, and this is a consequence of the transitive chain of dependencies that are pulled from the build system. And we found that another cause is the inheritance of dependency. It's this dependency mechanism of Maven in which you have multi-module projects and then you have dependencies coming from modules. And also the limited engineering of POM files. And we found that software developers care about bloated dependencies. They are actually willing to remove them. And the data, our experiments, confirm that once a dependency is bloated, it's very likely to remain bloated over time. So our empirical evidence suggests this. So there are some lessons that I have learned during my PhD, specifically working on software debloating. The first one is that debloating Java dependencies is a relevant problem. The second is that automatically debloat projects, which are really complex, is much more difficult than trying to debloat small projects. Like actually targeting big frameworks is much more challenging because of the number of dependencies, because of the complexity of the build mechanism, because you need to make sure that after removing code, the project is still built, it is still other tests pass, it is still deliver the same result, the same output. And also, we have learned that having a guarantee of the safety of the debloating procedure is very difficult in languages which are dynamic. Like, for example, in Java, there are many dynamic features that make this process very, very complex. For example, there is reflection, there is dynamic proxies, there are custom class loaders, which very much complicate this process of debloating. So, I have, on these years, done some contributions. I have maintained a blog, which in my personal website, which I have shared my journey, my PhD journey. I also maintained a living review of papers in the area of software development, which turns out to be useful for some researchers entering into this specific field. Of course, as a PhD student in KTH, we also do many activities. In my case, I have supervised three master theses successfully. I have also participated in a lot of teaching, like more than 15 different courses. And I have been also active as a reviewer for journals like Empirical Software Engineering and also conferences as well. And we have tried to disseminate our results to society. And we have done this mostly through the VAS network, in which we are part of. We have been traveling and we have presented our work in many continents, I would say. And through these events and talks, for example, I have participated in the FOSDEM, which is a very well-known open source event for the open source community. I have presented there our work, and we have got very good feedback. And also through academic collaborations. I have collaborated with more than 10 papers in which I am co-author with my colleagues as well. So, we have also tried to reach developers. We have been in companies such as Scania. We have been in the SL transportation company here in Sweden, where we look at the systems and try to motivate them to use debloating tools. And for the future work, we believe that it's a good idea to use debloating as a way to specialize and diversify the software supply chain of artifacts. Like this, for example, let's say that you have a project which has a dependency, in this case, dependency D, and then we can through debloating have multiple variants of this dependency D. For example, in this case, let's say that you have 3 variants, the 1, 2, and 3, and then you can, at the runtime, switch between these variants. And this is good because then from the perspective of an attacker who wants to attack the project P, then the project is going to have different versions of the dependency tree with different code for each version, for each variant of the dependency. So it's going to be very hard for the attacker to know exactly which code in the dependency has been used at every time. So this is one potential direction for debloating, and especially in running environments. We believe that the idea of debloating at runtime for systems that are actually running in which you can change the code by removing code at runtime is a great idea and is very promising. So my time is out now, and I want to just leave with this last slide, which counts 6 publications which are part of this thesis. And just in this presentation, I focused in the first 2 of them, but we have explored the software debloating for multiple angles. We have addressed debloating for dependencies, for applications. We have evaluated with respect to clients. We have analyzed the dependencies in Ethereum, Java applications, Java clients. We have analyzed the supply chain of Ethereum clients. We have used code coverage for performance dynamic debloating and also for specialization. And you are more than welcome to read these papers if you are interested in. So thank you so much for your time.
Thank you.